Well, we made it, folks. Looks like it's time to begin. Today, we're going to mainly discuss the homework system WebAssign using the book and show just a couple quick demonstrations on things you can do inside there. Then we'll go right back to section 2.2, continuing on in example 1. My goal in the day-by-day syllabus was to finish section 2.2 today, but I think it is important to spend a lot of time discussing WebAssign, just so that we have, well, we're all on the same page with that homework platform, answering all questions. So we'll take as much time as necessary taking a look at that. But before we start any of that stuff, any questions at all, folks, to start us out? Okay, well, before we jump right into WebAssign, let's start by kind of just imagining that you are a student in the class. I mean, that's easy for you. You literally are. But let's all imagine that you're coming in maybe on an ordinary week right before class. You're going to study some course materials before joining class. What I would do each time you go into the course website, Moodle, is just look at the current week, see what's going on. This piece of information here is always going to tell you what you should read before you take a look at the lecture notes. Not that you have to read that all verbatim, every single page there before you come to class, but just taking a look at that section, seeing what kind of information is there, that's actually super helpful for your mind. It kind of gives you a little structure in your brain of what's going to happen during class. And that way you don't feel like you're blindsided with every single new concept. So reading the book is a great way to go before you even start thinking about coming into class, doing any homework problems. And to do that, you would go all the way up here to the very top. And the textbook and the course homework system is the fourth link down, WebAssign. So let's click on that. And by the way, before I click on that, it looks like I think on my data, we've got about 85% of the class fully registered on WebAssign. So that's awesome. Congratulations, folks. If there's, for the folks that still haven't registered in there, it's either, let me see what I was going to say there. If there's any kind of weird difficulties going on, please don't hesitate to ask about it. So maybe that's a good question for the class at the moment. Has anyone had any weird issues trying to log into WebAssign? Any weird problems with the book bundle system? Okay, I guess silence is good on that question there, but if stuff does come up, don't hesitate to contact me either after class, before class, office hours, or just send me a direct email. I'll be very happy to work with you, get that sorted out as soon as possible. So let's go to the WebAssign link. The ISU book bundle link is pretty much ineffective for our course, and I can't actually delete that. It comes back like a possessed Ouija board. So it's just going to be sitting there. Click on WebAssign here to get into the homework system. And let me just sign in real quick. When I log in on a Chromebook, they let me know that my password was using a data breach, so I know I need to fix that soon. And this is about what you would see when you're joining into WebAssign. Getting ready to either do the homework sets, that's under my assignments tab here, or read the book before the lecture. So the ebook is way up here. We clicked on that before last class, but let's just click on it again. Clicking on that, I have to click on it again. That's kind of weird. But as long as it works, that's the most important thing. Directs us to a new website, MindTap. And then finally, that's your textbook right here. So if you missed that screen, let me go back a tab. Your textbook is located on this link right here. If you're in the book bundle program, they gave you an access code, and this is the way that you're getting your course material here. Then up here, navigating through the text is pretty much just point and click. We're in chapter 2, so click on that chapter there. It might send you to the right spot, but you're probably going to have to click the table of contents for the chapter. Go to section 2.2, and then finally, this is the book, like we discussed before. And like we mentioned, it's always good to see what we're going to discuss in class before coming to class, logging into Zoom. And any pre-reading you can do ahead of time is very, very helpful. Even it's, again, just kind of skimming to see what's on there. Say the definitions about limits, looking at some of the graphs that they provide. And when you come back to the textbook to maybe do a more careful reading, maybe you're studying for an exam, the best way to really read this textbook is certainly read the stuff in the middle, but once you get down to, let me see here, an actual example, not quite, oh, there we go, example 2. What are the horizontal asymptotes shown in the curve in figure 5? scroll down to this part, not to where the solution is. What you really want to do when you read these examples is just look at the question itself, try to answer it on your own. Actually, this is a good review topic for us, so let's just do this problem right here, pretending we're reading the book. This was essentially the first concept right before example 1 in our course notes. And I forgot how to do this. Hang on. There we go. So it's asking, what are the horizontal asymptotes of the curve? Well, it looks like there's a horizontal asymptote going this way. And this would be at height, y equals 3. So that would be its equation, y equals 3. Another horizontal asymptote comes through like this. So this would be at height, y equals -2. That's all they were asking on the homework, or excuse me, on the reading right here. What are the horizontal asymptotes? So after you write that down, I mean, maybe not necessarily annotation, just on scratch paper, then come down, take a look at what they said. Let's see, this means y equals -2, y equals 3 are the horizontal asymptotes. But you'll notice I missed something when I wrote that out. What they really want us to take a look at is what are those limits? But that's normal when you're doing a reading for the very first time. The idea is try the problem on your own, see what you missed, and then come back up and revise. So here's our second attempt at this. Uh-oh, let me see if this can go back. There we go. Looks like what they really wanted us to say was, let's put this in, maybe a better color that stands out. The limit as x goes towards positive infinity of f of x equals 3. This leads to that horizontal asymptote. And let me move this equation over here just so it's not so busy on the right. Y equals -2. And let me put back here the 3. Okay, so what I've done so far is we read the next part of the solution. We noticed we missed the concept of they really want us to do the limits when they ask these instructions here. So I wrote in the limit as x goes to infinity. That's taking, hang on, as x goes to infinity would be this direction, should have been -2. My bad on that one. Let me X that out. We'll leave it like this just to convey that was a mistake on my end, and we should have had -2. Let me actually put that back where it was. Sorry about the weird decisions on moving those asymptotes. And I want to put here just a little box to convey get rid of that. Then when you take the limit as you go to infinity, you're looking at this end right here, and you're always just picking up the value of the horizontal asymptote is the answer of the limit. So that's the kind of cool thing about this idea. The limit itself is the new complicated idea, but it's anchored with a familiar idea that the value of the limit simply the asymptote. -2 because we went in this direction when we said positive infinity. So we ought to do it again. Let's go and take limit as x goes to -infinity. If we go in that direction, that means we're following the curve up in this way. Towards -infinity just means your x values are going to the left forever without stopping. We're hitting another horizontal asymptote, y equals 3. So let's put in that limit as x goes to -infinity is just 3. Of f of x equals 3, and that's because of this end of the curve, that horizontal asymptote. So that's a great way to read these kinds of textbooks. The more active you are with your pen, pencil, piece of paper, the more this information really just seeps into your mind. Only using a limited amount of your senses, just your eyeballs to read it, that's a really, really hard way to learn. So try to involve more of your senses, be very active when you're reading this, and you're really saving a lot of time. You might notice that if you're studying this textbook at a high order way like that, you may only ever read these sections twice. But if you're a person that kind of skims through these as you study, you might have to read this quite a few times to see all the missing details. Let's actually take this whole thing right here, just because it's a helpful example. Let's put it in our course notes. Any questions at all, folks, with the computations here, however? Okay, I want to drop it into our actual lecture notes. So let me go here, 2.2. These are the lecture notes that we worked on just yesterday. That looks kind of crazy. Let me clear that, annotate. And in case that was a helpful example you want to take another look at, we'll just drop it down there on the lecture notes. Okay, so what we were doing so far in class is just going through the textbook, showing how to use it, that kind of stuff. But mainly our objective is to discuss WebAssign. So let me close the book, back to WebAssign. And here, when you're logging in just to do the homework, presumably after you did a little bit of reading before the lecture, then after the lecture itself, that's when you want to jump down here and start working on problems. Keep in mind though, until we completely finish section 2.2, there might be some problems there that we just haven't gotten into. Typically the ones at the very end of that section, for example. But if you'd like to give an early start on this, even before we finish section 2.2, that's definitely a good idea for just staying caught up. So to do the homework, just click on the link right here. There we go. And this is the assignment. It gives us some information about when it's due. You can request an extension at any point in time. I'll talk a little bit more of that after we get past the first due date on how to get extensions and that kind of stuff. I don't have a late homework policy, so the due dates, they're mainly for the sake of pacing. If you don't get it done by the due date, your score will drop on WebAssign, but you can always request an extension, come back to that material and finish it out free of penalty. So that's mainly to give us some flexibility because this is a highly non-traditional class, for example. And I find that that's a great way to work this kind of system. You can click on any one of these questions, but I think a lot of people are just going to scroll down to the first one. And it's pretty much like any online homework system. You analyze a problem. It's meant to be similar in the textbook. It says determine the limit as x goes to infinity of f of x. Well, that means we'd be following this curve along that path and saying what the value is for the height of the curve as it gets further and further to the right. Anyone happen to spot what the limit should be for this one? 0? Absolutely. Limit as x goes to infinity means, let's actually kind of draw this in just to emphasize. Because it said x goes to infinity, we're concerned about this part of the curve to the far right. So limit as x goes to infinity of f of x is, because we're getting closer and closer to the height of 0, it would be equal to 0 itself. So that means all we're going to do is come up here, drop in a value of 0. If the limit doesn't exist, we would put it in DNE. We'll just have some examples like that. Click submit answer, and we're on our way. Check means we're all set. You could go down to the very bottom at this point and, oh, never mind. There used to be a button where you'd save the assignment. But my comment for that was, it kind of is irrelevant because the minute you hit submit answer, it records the result. And so it's saving each time you put in some information into WebAssign. So there's no weird issues where you can work huge part of the assignment and lose all of your data, having to redo it. It's pretty good about maintaining all that information. So sorry for doing the entire first homework problem, but it's good for a demonstration's sake. And if you were, say, working a harder problem, maybe something like this one, and you felt like after you're working this on your own, you just are not sure how this goes, definitely, well, you have two things you can do. You can show me the work that you have on paper, maybe scan it or take a cell phone picture, send it to my email and say, hey, Mike, I'm not sure why I'm getting this wrong. Is there a step I'm missing? I'll be very happy to look at your work and diagnose it with you. Or another option is click this button, ask your teacher. You can say anything you like here that's helpful. You can say what you've tried. You can say what seems to be going on but doesn't seem to work. And it can even just be something like, hey, Mike, I should be able to spell my own name. Hey, Mike, I'm lost. That's something like that. That's totally fine as well. I mean, that's good information for me. Click on send. And you have to be a little bit patient because then what this does is it's going to bounce an email to my ISU email account. I'll go into that account, see this message, and get right back to you. In fact, let me show you what it looks like just from my end. I go back into WebAssign. Or sign in again. Maybe they remembered me. Hey, now since someone had a question, I now have this notification here. I'll click on this. Oh, that's not how I usually open it. I'll click on this right here, the unanswered question. This came from me. I'll be able to see what you tried out before, if there were tries. I'll see the exact question you're looking at. By the way, the numbers are red are just saying those are values that can be randomized from problem to problem. And I'll be able to say something along the lines of divide all terms in numerator and denominator by the highest degree term in the denominator and go from there. Notice how vague that is. If this is not helpful for you, you can go back and say, I'm still lost. And then I can try other things to help you out. I might end up sending a direct email to your ISU email account with a little more stuff like graphics, for example, because I'm pretty limited in the typesetting over there. I can't do a whole lot. I don't think you can even italicize anything. So if I need to give a little bit more response, if my first one didn't help you out, keep on asking. It's my job to resolve these questions. So my first response is vague. Maybe I just opened it up really early in the morning, hadn't had my coffee yet. I could have made a mistake or just missed something I should have said. So that's the way to do the homework. That's how to get extra help. Any questions so far at the moment, folks, about working with WebAssign? Okay, maybe one more thing I want to, oh, it says right here, new message from your teacher. I didn't really know that that's what it looked like. Let's click on that. So after I responded to you, I've never actually seen this before. Click on that, and what does it say? Just new message. I'm not sure how to open that up. Let's see here. It would have been on this one. Oh, that's helpful. There's a little red flag. So when we click on that, here's the unread message. And then if this is helpful, fantastic. And you might say, if it's not, this isn't helping me. Anything like that's just fine. You can say, I tried it and it still said this happened, describe what the difficulty could be. But if you still feel totally lost, no harm on just keep on asking questions until we land on the thing that gets us to work out right. And again, like I mentioned before, I might give you an email of check your ISU email. I gave a description with a diagram, something like that I could give. So that's working the system. There's a little bit more I want to talk about demonstrating how to request homework extensions and things like that, but probably best saved for next week. Well, that's my, I guess, nearly 20-minute demonstration of WebAssign. Any questions or comments at all, folks, whatsoever? Okay, let's close this out. And that was the major thing I want to discuss today. Again, if you have any issues getting registered in WebAssign, don't hesitate to reach out. I'll be very happy to provide support. Other things to keep in mind are, let's see, the recorded lectures are getting built out day by day. So if you ever had to miss a class, maybe you had to leave early or maybe you came in late, it's all going to just be dropped into this this playlist right here. There's a lot of things I mentioned before that I have to do after class to make sure files and videos end up in the right spot. So if something looks like it's missing, let me know right away and I'll make sure to get it fixed as soon as possible. And what else have we got going on here? Also, the blank lecture notes. This is purpose for if you want to print out assignments or download lecture notes before we start working on them. This will be the one-stop shop for all of the blank lectures. Well, thanks for bearing with me through all that, folks. There was a lot to talk about last class, so I felt like it was good to kind of break it up across two classes on working with WebAssign at least. With where we're at now, we're just working through this document here. So let's get started in earnest. We go to, let's see, 345. So here's where we left off. Well, this was the problem out of the book. We left off here on trying to answer the question of what is a derivative. This is a pretty confusing graph on day one. So if it didn't quite make a whole lot of sense, no worries. We're going to loop right back to this and do another graph along these lines once we're done with limits in chapter 3. Then next, we analyze this definition here of taking limits as x goes to infinity or negative infinity. And this is finally example 1. This is a problem that could be a potential quiz problem. We'll have weekly quizzes, but I didn't sign one for week one since we have a lot going on with registering for WebAssign, just getting used to the course. But once we start to see things like example one, these examples could be potential quiz problems as well as potential exam problems. I would change the graph and change some of this stuff here, but very similar in spirit. So it says here, the line y equals L is a horizontal asymptote of the curve if either the limit as x goes to infinity comes out as L, or is the limit as x goes to negative infinity comes out to L as well. So the idea here with this definition is a horizontal asymptote is synonymous now with either one of these limits having the value L. So let's connect those dots on example one. It says we have the graph of a function provided below. And notice it's like three distinct curves, but all together this forms up the graph of one entire function. So you could call it, for example, y equals f of x, which comes into these three different parts. We want to know the value of these following limits here. The limit as x goes to infinity, and the limit as x goes to negative infinity. But those limits are all about the direction. Every time you read a limit statement, look at the part down below. If it says as x goes to infinity, that means we're concerned about this side of the graph over here. Any volunteers for what that limit should be? Yeah, absolutely. It looks like it should be a value of 1. Notice, though, this is kind of tricky already. If you're thinking to yourself, well, that looks like it's about 0.95. I would accept that as an answer. But really what this graph is trying to say is all the relevant information is contained in this window. And it seems as though this curve is getting higher and higher, closer and closer to the height of 1 as x gets larger and larger, moving to the right. So if you say a value of 1, that'd be the value that's typically expected. That'd be the value that WebAssign wants. If this was a real exam question, you said 0.999, that's acceptable to me as well, since we're just doing this as a graph. And your answer just has to be in the right ballpark. So we looked at this end of the graph to get that limit. Let me just say it here, just for connecting the dots. From that portion, it's telling us limit as x goes to infinity, f of x is positive 1. So that's one limit down. We'll do it again. Here we're just going to the left. Really, that's our limit so far. Either go far to the left, negative infinity, or far to the right. We'll do other limits in further sections where it's the limit as x goes to, say, 5, for example. But for now, it's all about these kinds. So if you're going towards negative infinity, you're on this end of the curve. And it's kind of a strange looking graph. It's oscillating, but the amplitude of these oscillations are getting smaller and smaller. It's damping down. That means this curve is getting closer and closer to a height of, looks like 2. Does that make sense to folks so far? Awesome. That means we just paraphrase this whole thing and say the limit is 2. And just to give some parallelism in the notes, this part of the graph and only this part is where we got that limit. As x goes to critically now negative infinity, f of x is 2. So that's our content that we looked at last class, just doing these kinds of limits. The new idea up here is now telling us information with asymptotes. But question first? I see what you're saying. Yeah, it's oscillating onto, but if we say extended the graph going this way, it looks like what they're trying to do to that graph in spirit. Let me see if I can get a similar color. Maybe this one. Looks like what they're trying to say on this graph in spirit is that the isolations are getting so damped that the curve is more or less doing this, just getting closer and closer to height 2. Starts with a big oscillation here, but the heights get smaller and smaller. It looks like it's compressing down towards this line, y equals 2. And that's what gives us this valuable limit here, 2 for negative infinity. But does that help to visualize it in that sense? Awesome. But you know what else we could do with this one is, let's open up a quick graph. Let's see if we can come up with our own function to see that does something along those lines. I want a function that does this kind of weird squiggly behavior going off to the left, but settles down to some finite height, like the height of 2. Let's see if we can come up with that. So it should be something like y equals, let's make it be 2. We're doing great. This automatically has the limit as x goes to negative infinity is 2, limit as x goes to positive infinity is 2, because the height of the curve is always 2. So let's add a little bit of extra drama to this. We don't need to know trig on this course, but this is just for the sake of demonstration. Let's put a trig function in there, sine x. Now it's oscillating, but not like this one. The heights of the oscillations were being damped down. On this one, it's just going up and down by the same height forever. This is a good graph to add to the notes because we can also say here, to use that color, limit as x goes to negative infinity of f of x does not exist. We use DNE as a shorthand for that. Does not exist. And the reason for that is, for the limit to exist, the height of the curve has to settle down on some number. But it doesn't matter how far you go off to the left, it's always going between, looks like, whatever that height is and whatever that height is. Negative 14 and, hang on, positive 2, negative 2 is where it's oscillating between. So we want a graph that does this. The limit is actually a value like 2. So let's do a little bit more. First, it's important to know when limits don't exist. So let's add this as its own example. Put it somewhere safe, about right here. Okay, one more try on this, folks. Now, to get this to damp down, so it looks like the limit would exist, we need a whole new function. Let's multiply this by e to the power of negative positive x. Let's go positive x. Some bizarre behavior on the right. Doesn't look like the limit is going to exist. But now on the left, if we follow this, sometimes it's below the x-axis. Here it's at negative 0.2. Other times it's above. It's at positive 0.2. Let's see here. Let's keep on going to see if it goes below. Yeah, right out here. It's below. Oh, hang on. It's kind of hard to hit. There we go. Right over here, it's below the x-axis by 0.00005, probably a rounded value. Now it's above. But in this case, we would say the limit does exist. The limit is 2. Because the further and further you get to the left, hang on, let me see here. It looks like the limit is 0, rather. The further and further you get to the left, the closer and closer it gets to 0. This value really isn't 0, but the numerical precision of Desmos has failed. It's just rounding to 0 at this point. So that's kind of the idea of what's happening here. Even though it's going above and below a horizontal asymptote that we see, as long as it gets closer and closer as we go to the left, the limit will exist. Definitely kind of a tricky problem because of the weird graph. Any questions about it at the moment? Okay, now finally, the punchline to this is really more about the definition above with horizontal asymptotes. Let me see if I can scroll to a reasonable amount here. There we go, that ought to do it. So now finally, it says if you have a horizontal asymptote, the limit will exist and give you that value. Vice versa, if the limit exists as you go to positive or negative infinity, it means you had a horizontal asymptote. So right here from this one, we went to positive infinity, got a limit of 1. So a horizontal asymptote would be y equals 1. Then finally on this one, we went to negative infinity. The direction is irrelevant, it just has to have an infinity on it. If you have a value here that existed, the other one would be y equals 2. And we can add these to the graph. Here's y equals 2. And here's y equals negative 1. So again, major purpose of example 1 is connect the concept of limits at infinity with the horizontal asymptotes. Any questions or comments so far with this one? Okay, well, let's keep on going. I think I said this class ends at 3:45. I don't think that's accurate. We go from, no, wait, 2:30 to 3:45. That's right. For some reason, I thought we started at 2. I'll get used to my schedule eventually as we get through the semester. Well, let's take a look at another example. The idea with what we did on these first set of examples is we're trying to understand the limit as we go to infinity. And in calculus, it's always best to try to connect that with something you can actually see. Because later on, we want to do these same limits with functions which are ungraphed. So this is the major objective. Evaluate all of these limits down here using nothing but the algebraic expressions, as well as the good old limit laws. That's a lot of stuff, like we mentioned last class. But think of this as very analogous to when you're given a set of exponent laws. There's like 15 different exponent laws, depending on how you count them. But the idea is no student really tries to memorize every single exponent law verbatim. What you do is you just practice problems and you learn what can you take for granted with exponent laws, what you're allowed to do, and it becomes second nature after a while. But you do have to state what the exponent laws are. It's the list of things you can take for granted. And this is now the list of things you can take for granted when it comes down to limits. I will provide this set of limit laws on the real exam 1 as a formula sheet. But again, our idea is just become familiar with this kind of stuff. Let's look through some of the points. What it's telling us is if you have multiple functions in parts 1 and 2, maybe you're adding 2 functions together, then the limit of a sum of a functions is just the limit of one function plus the limit of the other. Same for taking a difference. Limit law number 3 is a little bit easier to describe. It says if you have 5 times a function and you're taking the limit as you go to infinity, you can break this up by saying do the limit first and then multiply by that constant c. Maybe it's the number 5, for example. The limit of a constant is itself. We kind of looked at that one a little bit on Desmos, where we were saying y is equal to just 5. Then the limit of this, as you go to either positive infinity or negative infinity, it's just going to be, I said y equals 5. Looks like it's y equals 6. It's just going to be 6 because that's the output all the time. So some of these things are just showing us what we would expect to see with limits. Other things are a little bit trickier, but you can think of this almost as a type of distributive law. We have a distribution across addition. We have a distribution through multiplication. That's surprising. Add division, limit of a quotient is just put your limits, do the numerator, denominator separately, and it'll exist as long as g is not 0. This one's a trickier one, but we'll take a look at this as we get closer. And this might be the most important one in the whole set. So it deserves some highlighting and maybe a graph to go along with it. So this limit is telling us if you have a function that goes like this, f of x is 1 over x to a power p. I need to give it a real power. So let's start with maybe squared. Then it's telling us if you go to positive infinity, and this is true for negative infinity, the limit will be 0. Let's take a look at that. Focus on the second coordinate, 4.7 currently. I'm going to take the limit as x goes to infinity, so the first coordinate gets larger. And notice how the second coordinate gets smaller and smaller. Currently 0.05005. But we can make that as small as we want by just making x ever larger. So now it's currently really small, about 0.021. But this is only if the power p is positive. So what if we go like, say, -1? This limit doesn't exist now, because if you're going off to positive infinity, the values on the second coordinate will get larger and larger and larger. There's no number it settles on. It just grows without bound. What went wrong? The power was negative, not a positive power like indicated here. So even if it's say 0.1, notice this is getting closer and closer to 0 as you go off to the right, even for a very small value of the power. It just had to be positive. And the further we go to the right, it's going to take a while, the smaller and smaller these values get. I'm now at 0.58 when I'm at 215. Or another way to view this limit is what it's saying is, if you have 1 over, say, 5, you're getting a 0.2, but the power is bigger, your denominator is going larger. Now it's 1 over 50, but x is going off to infinity. You would make that ever larger. And notice the output is getting ever smaller. That's what's being conveyed here. As x gets larger, the value of 1 over x to a power goes to 0. So again, that's probably the most important concept right here, because we're going to use most of these properties together with property 8 to evaluate these limits starting on part B, part C, and so on. I'll cite these as we use them so we can get good familiarity. And let's start then with part A, example 2. Any questions first, folks, with the limit laws? Okay, so this one is already right out of the gate kind of an annoying problem. It seems like it fits property 8, but we have trouble with the radical expression, that square root x. In this class, we're going to learn a lot of exponent laws, so let's just start writing out the exponent law we need here on part A. Square root symbols are usually not too friendly for us in calculus, so we usually use this idea. The formula goes, the nth root of a is just a way to say a to the power of 1 over n. And if it's written just this way, square root of a, similar to what we see by the red dot, then that's just saying we have a to the power of 1/2. So these are critical ideas for whenever square roots come up. They'll come up a couple times in the homework as well. And what it allows us to now do is say, this is the limit as x goes to infinity of 1 over x to the power 1/2. So we can now use property 8 because we know the power p. The power p is this 1/2 right here. It does satisfy this property. It's greater than 0. And that means our work is done. The whole limit has to evaluate to 0 because the denominator just gets bigger and bigger and bigger without bound, giving us a closer and closer to 0 quantity. We won't have graphs if we're doing this as an exam problem, but when you're studying this, maybe in WebAssign, maybe reading out of the book, or even doing a quiz, you ought to use a graphing calculator or this website Desmos just to visualize if you're on the right track, what's really going with your value here. So let's put this in just to visualize. F of x is 1 over x power 1/2. And hang on here, I need to get a better window to show that. There we go. That's a little bit better. The graph of this function, 1 over square root of x, looks like this. And yeah, certainly as x gets larger and larger, second coordinate becomes smaller and smaller. And we can make it as small as we want just by making x ever larger. So we convey that whole set of information by saying the limit is exactly 0, even though the function itself never actually hits that value. But any questions at all, folks, with that part A? Yeah.
Yeah, so if it's a cube root of x, it would be 1/3.
Exactly, yeah. For a very similar related example, it could have been lim x goes to infinity, 1 over cube root x, and maybe it could be even more fancy, like cube root x squared. Then this would be limit x goes to infinity, 1 over. So if you have a power 2 here, you're taking a cube root, this would turn into x power 2 thirds. So the critical thing that's happening is whatever that is forms a denominator. And if it's missing, like over here, the denominator is 2. Yeah, question over here? Yeah.
One and not in the like 1 over x to the power and then plus a number. Would the limit then change to that number that you added to?
Yes, absolutely. Yeah, that's a great question. Let's put that down as another related example. I'll put a little border here to say part A is done. These are related questions, very good questions to ask. And let me know if I've got this one right. Limit x goes to infinity. Let's make this be 1 over, how about another weird one? Fifth root of this time just x, and you're saying like a +1 here, or are you saying a +1 in that way?
I was thinking that way, but I didn't either or.
Gotcha. Let's go for this one. So the idea with this limit here is now we're really using limit laws. So let me scroll up here. In fact, let me do something that might be more efficient for us. Let's open a new document. I'm just going to paste these in so we can screenshot them in a little faster way. Okay, so we've got our limit laws here on the right. And for this one, the most relevant limit law is going to be limit law number 1, because we have two functions. This would be the f of x, and the plus 1 would be the g of x. It tells us we can break up the limits in this kind of way. Let's put it right under here just to convey we're about to use that limit law. So the f of x is that whole function. The g of x is not really the plus, but it's that function, the constant function, identically equal to 1. So now it means we'll get the limit as x goes off to infinity of 1 over x to the power of 1/5 coming from the 5th root plus limit as x goes off to infinity of the constant 1. So we've got this one down. That's property number 8. They'll go to 0 just like part A did in the related example. But this limit is a little bit vague in a certain sense. Any volunteers to say what would happen to that limit? Yeah, it's going to be that constant 1 because it's a horizontal line if we were to graph it. And the related limit law for that one would be limit law number 4. The limit of a constant is itself. Let's paste that in as well. So this affects that part right there. And we now say we have a limit of 0 plus 1. So just now 1 altogether in this case. All the questions at the moment with that one? Okay, so part A and the related examples down below is us just getting started with using property number 8, as well as the other limit laws. But then when we go down to some of the other examples, they start to look a little bit more complicated, like this one down here, 5x minus 9, 3 minus 7x. Now, depending on how fluent you are in college algebra, rational functions, and their horizontal asymptotes, you might be able to just eyeball that and see the number. If you're not too familiar with horizontal asymptotes, if it's a little rusty, that's totally fine. There's an algebraic procedure to find it in either case. So let's give this one a try. Let's put down some comments on how to even start off one like this. So step 1. This is a rational function because we have a polynomial in the numerator, polynomial in the denominator. So this is rational. If you see a rational function and you're taking a limit as you go to infinity, what you need to do is go to the denominator and find the term with the highest degree x, or let's just say the highest power on x. So that term in the denominator isn't the first term 3, that's constant, so it would have degree 0, the power 0. But over here at the negative 7x, that's the term with the highest power of x. X is to power 1 here. So we grab that x. So next, divide all terms by x with that highest power. So that's step 1 for our procedure. So for example, on this one, we're dividing everything by x. All terms, numerator and denominator. Part C we see down below, we'd be dividing all terms, numerator and denominator, by x cubed, since that's the highest power term there. So this is all about the denominator. There could be crazy stuff happening in the numerator, but for this limit to exist, that x as well as this x cubed are the most important things. So let's go and write out that step. It's limit x goes to infinity. We're dividing everything by x, so I'll start off by just writing it in. 5x over x. If you put 5 down here, that's completely appropriate, but it just makes the notes a little bit more harder to read. So I usually show these steps in the middle. So minus 9 over x. Then the whole thing is divided by 3 over x minus 7x over x. Next step you need to do is just simplify what we've got now. So now it's limit x goes to infinity. In the numerator, we have 5 minus 9 over x. Then finally in the denominator, 3 over x minus 7. Let me put a little bit of extra space down there. So this is where we would want to be with our limit laws. And here's what's going to happen next. Sorry about that. Let me move this over. Find a spot to move it to. We need to use a bunch of limit laws to run through this whole thing. The first thing we're going to do is this limit law right here. Because we have a fraction, we can take the limit of the numerator and the limit of the denominator all at once. So we'll apply limit law 6 to start. Let's say get a good screenshot on that. There we go. So we apply that to this portion right here, and we are left with lim x goes to infinity, 5 minus 9 over x, divide by the limit as x goes to infinity of 3 over x minus 7. So that's limit law number 6. And by the way, what I do want to mention about what we're doing here in part B is we're mainly just trying to explore what the limit laws are trying to say and how to use them. But when we really do these kinds of problems, it actually goes a little bit faster. So I'll do part B in a couple ways to show using the limit laws verbatim like we're doing here. And then another approach where we show what do people do in practice once they have done these limits a lot and they're more familiar with the limit laws. Because this could be tedious if we did it this way each and every time. Sorry, let me try to fix this window here. The next thing we have to do is, well, we have 2 terms in both of these limits that we're looking at, and this is relevant to us. We can essentially distribute the limit through these both terms in the numerator and the denominator and calculate the limits independently. So by next property 2, property 2 applied here. Again, this is kind of tedious. We will not do the limits this way every single time. More of a demonstration. But it turns into this now. Limit as x goes to infinity of 5 minus limit as x goes to infinity of 9 over x. So that handles the numerator. Now for the denominator, same idea. Limit x goes to infinity of 3 over x minus limit as x goes to infinity of 7. So we had 4 terms, numerator and denominator in total. So if we use a whole bunch of limit laws, we would get 4 limits in this kind of way. Now, some of these are pretty rapid to do. For example, this one and this one, these are just limits of a constant. They're just going to be 5 and 7, and that's through limit law 4 we discussed earlier. So those are the fast ones. But you might be a little concerned about limit as x goes to infinity of 3 over x. Because what we're trying to apply to that one is property number 8. And the most salient feature about property number 8, the way it's written down is, it's a 1 in the numerator. How do we reconcile with the fact that there's a 3 here and a 9 here is through limit law number 3, our first use of it. Limit law number 3 says if there's a constant that you would rather just eliminate from the limit expression and put it in front, go ahead and do it. So let's do that ourselves. So down below, limit law number 3, this is turning into kind of a spaghetti diagram type of mess. What's meant to handle this portion as well as this portion at the same time. So we'll get actually, let's do some of these limits. We mentioned this is a limit of a constant, so it's just 5. Over here, we're using limit law 3, taking the constant 9. That constant 9 is playing the role of c, you see over here. Actually, there's no harm in conveying that better. We're moving those constants away, so we'll get minus 9. Limit x goes to infinity of now a 1 over x. That puts property 8 on the table for us. Divide by, let's do it again. Property 3 says that 3 can move out in front. Multiply by the limit x goes to infinity of 1 over x. So that part's done. This is the limit of a constant, so it just turns into minus 7. So that's what happens with 2 limits so far. Now, all we now need to do is the last property on that list to handle this part and this part. Any questions so far, folks, to this stage? Yeah. Pretty much what we're going to do, yeah. The way we usually use property, didn't mean to do that. Property number 8 is just a cancellation kind of property. So let's drop it in one more time. And the way it's used is, let me just point to where we're using it. A lot of times when people use that property, they write down this on paper. It's a cancellation, but because it's through a limit, we're saying it cancels or the limit becomes 0. It's just gone now. This is a cancellation as well. The arrow says that that limit converges to 0, as well as the constant in front of it. Let me write this a little bit better. This whole thing goes to 0. It's really a negative 9 times 0. And same here, it's positive 3 times 0. So that means all we're left with is 5 minus 0 divided by 0 minus 7. And the value of the whole limit is negative 5/7 after that long, kind of drawn out process. So we started from here, and after taking all of these careful steps, negative 5/7 is our result. Let me reiterate what we said before. People don't do limits this way every single time. The reason we did it this way was just to say, how are the properties from the limit laws actually being used? Another takeaway is, let's go back to that college algebra thought. Actually, I kind of want that staying there. If you think of this as a rational function, there is a tie in the degree of x in the numerator, degree 1. Degree of x in the denominator is also degree 1. So what we actually expect here is, let's get another color, 5 and negative 7 should come down here. It's not a coincidence at all. So the more you know about these kind of horizontal asymptotes, the faster and faster these problems could be. But like promised, this is kind of a tedious way to do this. So here is method 2. Any questions whatsoever, folks, first, before we see this from a different view? Okay, let me call this one method 2. Let's say that this is more practical. In method 2, if we're going to handle this limit, and we're still going to use the approach that our author shows of focusing on the denominator, we'd begin by writing limit x goes to infinity. I'm dividing everything by x. We did that once, so I'll skip a step and just put a 5 here. Then minus 9 over x. Over here will be 3 divided by x. I think I accidentally spit on the monitor. Then minus 7 after you divide by x. So that's a step of division and then cancellation. Then once we see this, our limit law properties are essentially telling us this limit affects that part, that part, that part, and that part all at the same exact time. And so in practice, that's what we do. Allow the limit to affect all terms simultaneously. But as you do that, property number 8 here says, this part goes to 0, it's just gone. And that part goes to 0. Really, it's through properties 3 and 8 simultaneously. We don't always show that step every single time. We just go here and write now. It's 5 minus 0. 0 minus 7 for a limit of -5/7 once again. So that's our method 2. Any questions, folks, with doing it in this slightly more streamlined way? Yeah.
So whenever the X is on bottom and there's a number greater than 1 on top, you just go straight to 0. Would that be the case?
I gotcha. Yeah. So really the bigger thing that controlled why it went to 0 was the exponent of P was bigger than 0. And the exponent on these were both a 1 and a 1 right here. So that's the part that allowed it to become 0 in the end. Does that make sense there for those two? Awesome. So
what's the primary difference between just finding the horizontal asymptote of the equation and finding the limit?
None. That's the great thing about this. So there's really no fundamental difference. A horizontal asymptote is conveying as you go off to infinity, the function values is settling down to a number, and vice versa to negative infinity. So that's what's leading us down to method 3. If you know the horizontal asymptote, you are done. You actually don't even have to do any of this. It's kind of fantastic. Does that make sense with that question there?
Yeah.
Awesome. Let's call this then that method 3. Using knowledge about rational functions and their horizontal asymptotes. Again, example 1 was telling us the horizontal asymptotes relate to the limits at infinity. There is no difference whatsoever. So if we took this whole problem right here, and we're going to analyze this through the horizontal asymptote, the most important thing is there's a tie in degrees. Whenever that happens, you will always get 5 over -7. Let me try to show this in a better way. We take the coefficient of x in the numerator, coefficient of x in the denominator, and literally drop them in. That's the value of that limit. It could be something like this as well. Limit x goes to infinity of maybe it's 12x cubed minus 17x squared plus 9. Looking like a complicated limit already. Minus 33 plus 41x plus 3x cubed. If we were doing this limit and we use the same method 3 right over here, we would want to analyze what is the degree of the numerator, degree of the denominator. Numerator is degree 3, and so is denominator. That tells us we have a tie. That means that it will be a horizontal asymptote of this automatically, found by grabbing coefficient 12, coefficient 3. And so now we're done. The result is 12/3, giving us a value of 4 altogether. So again, lots of ways to do these kinds of limits. I'd say method 2 is practical because the function might not be rational and it's still a good approach. Sorry, question up here?
Yeah. So basically what we're trying to say is that if you see it and they're tied, it can just take 3 seconds and ignore all the other values and just take the values of whichever x to a certain degree is tied with the other one.
Yeah, absolutely. So the question in class is, we notice it's a rational function, tie in degrees above and below. You can skip all of these steps and just grab those coefficients. Is that what you're saying? Yeah, absolutely. You're encouraged to do that if you see what the horizontal asymptote is on a real quiz, a real exam. If this was a final exam question, I would say this is the nicest, slickest approach. And once again, it's all about that definition right here. Doesn't seem like it was super important at first when we read it, but it is a pretty big statement. Horizontal asymptotes, totally synonymous with these two limits existing. So it's a good definition to come back to. In fact, let's add some emphasis. Hugely important. Well, that's kind of maybe being a little bit dramatic on its importance because you do have other ways to calculate these limits, but it can be a really big help, especially if you do use method 2 each time. You can think about that idea of horizontal asymptotes to determine, is -5/7 even reasonable? Well, the trouble with method 3 is Finding the horizontal asymptotes of rational functions does require a good amount of practice. Part C is totally different from what we did in these all other earlier examples. Anyone happen to know what the horizontal asymptote is of that? No worries if you're not sure. We're going to review that and use method 2. In the reading, you'll notice that author pretty much always exclusively uses method 2. And it's not a bad idea because sometimes our functions are pretty weird. For example, that was a weird function. It's not a rational function whatsoever. And so if you're going to analyze the limits of this algebraically, not through the graph, you really would want to use the method 2, our author's approach of dividing things from the denominator. So that method has its purpose. So let's practice it right here. Then we'll say what the shortcut method is as well for folks who prefer to think in terms of horizontal asymptotes. Our strategy, always just go to the denominator. When you're in the denominator, you're looking for the term of highest degree. That's the one involving x cubed. Even if it was 5x cubed, we're only dividing by the variable x to a power. So everything here gets divided by x cubed, which means we have a bit of an issue with that. Let's do some exponent work on the right to show what that would look like. We're going to eventually divide square root of x by x cubed. That's definitely its own little exponent law problem. Depending on how rusty you are, this might be no big deal or horrendously confusing. So let's get through this right here. First step is we don't want the radical notation. We go to exponential form. And we'll recall what the power should be on x here. Exactly, this ought to be 1/2. Then down below, it's to a power 3, but we need to use an exponent law here. That's going to only interact well if we make it have a denominator of 2 as well. So we're multiplying that 3, the exponent, by 2/2. It's now x power 6/2. We didn't change anything. Equality here is still maintained because that reduces back to x cubed. Separate exponent law we need. There's so many of them. Goes like this. Let's put it down below. If you take something like a to the power of m over a to the power of n, you can rewrite this whole thing as 1 over a to the power n minus m. We like this property because we're thinking in terms of property 8 here. We're trying to shove our expression down into the denominator so we can take the limit at infinity. The other way to do this, not as relevant, but still important, is a power of n divided by a power of n is a to the power of m minus n. So the subtraction is different whether you put your base to the denominator versus the numerator. Up here, we're going to give this a try. Using this one right here, the annoyance is you have to do the fractional arithmetic all at the same time, but no big deal. It's x to the power 1 over x to the power 6/2 minus the 1/2. So now it's 5/2. So that covers the most annoying part of dividing the square root by the power x. I think there's one just like that in the homework assignment as well. So with that out of the way, we're ready to get started on this one in earnest. But any questions, folks, with the exponent laws? Okay, let's get started then. First step, I'm going to write this out just to give a paper trail of notes. If you simplify as you go, no harm done. This turns into the limit. X goes to infinity of x squared over x cubed plus 4 root x over x cubed. We did that on the margin over here. So we're just going to drop in 1 over x power 5/2 when we go to simplify that. Then x cubed over x cubed minus 6x over x cubed plus 1 over x cubed. Let me highlight this in blue just to show that's us taking x power 3, highest degree power of x in the denominator, and dividing all terms numerator and denominator by it. Messy at first, but now it cleans up pretty quickly. It's the limit as x goes to infinity of, over here we have a 1 over x. Plus, from this one, we're going to use the work on the right and just drop in 1 over x power 5 halves. Then finally, we have a 1 minus 6 over x squared plus 1 over x cubed. So we're just about there. At this stage, we go back to, oh, sorry, let me move this around. Property number 8. Again, we use this a whole bunch. Anything that has x to a power, and that power is positive, will go to a 0 in the limit. Let's write in some of the powers for the ones that are missing. If you have just x, it's really power 1. What did I do there? Huh, that's kind of strange. So this per term, 1 over x, it'll go to 0 because we have a 1 here greater than 0. Similarly, 5 halves, I'll go to a 0. And these two as well for the same reason. Powers are 2 and 3 respectively. So all that to say, this goes to 0. This goes to 0. That goes to 0, and so does that. Not too much left over, but thank goodness that's still there. If you have 0 over 0, the whole thing's undefined. The limit did not exist. But we have 0 divided by 1, which means the value of this limit is exactly 0. This then tells us that thing up there had horizontal asymptote 0 itself. You could have just wrote equals 0 if you identified that. Well, any questions at all, folks, on getting through that one? Yeah.
What happened to the 4 in front of the x?
Oh, good call on that one. I think I forgot it that entirely. Looks like I was trying to focus on just the variable part, but I should have went like this. Or should have been copied in here, here, and here, which means it comes back over here to a 4 like that. Thanks for spotting that one. That was my omission on this. Let me highlight it in yellow here. So yeah, that 4 should have just been copied down. Looks like I just lost track of it when I was doing the scratch work over there.
You just take the 4 out and include 0 anyway, and then you're left with a 4.
Well, this whole thing would go to like a 4 times 0, so it'd just be 0 altogether. Thanks for mentioning that, though. Yeah, these are always tricky when there's extra constants going on, especially if you forget them. Other questions at the moment? Okay, let's call this another method. Just to convey, you can also do it this way. It's totally fine. You can't lose points for knowing stuff. And our author literally does say the value of this limit is its horizontal asymptote. So let's go down here and say 0. Done. If that's a real final exam question, for example, that's for full credit because that's really all it takes. Let's add a description here. Since the denominator has higher power, than the numerator, we now know that y equals 0 is the horizontal asymptote. I'll abbreviate that to just asym. So that means if it's a horizontal asymptote, the value is just 0 automatically. It is tricky because, again, we have to know knowledge about rational functions. And this is not strictly even a rational function, really, because of the square root right here. It's a slightly different kind, but it still obeys that kind of property due to the high degree in the denominator. And looking down next on part D, totally reverse situation. The higher degree term is in the numerator, not in the denominator. So this one would be a whole new approach in and of itself. But any questions at all, folks, with either ways of doing these? Okay, I guess the big takeaway point is when you see a problem out of the wild, maybe it's a quiz problem, an exam problem, WebAssign problem, always look before you leap because sometimes really isn't that much steps at all. And on this one, any volunteers for the class about what could happen to the horizontal asymptote here, if there even is one? It would be infinity, absolutely. Here, the numerator is of higher degree than the denominator. That means as x gets larger and larger and larger, that term right here, 2x power 4, controls this whole thing, and that part goes to infinity as well. So if you just wrote equals infinity, that's a totally fine expression for this one as well. Let's try our author's method just one more time, and we'll call this one the last problem of the day. Any other questions at the moment? Okay, so here's what our author would do. Once again, go to the denominator. The highest degree term is x squared down there. So we'll go take limit as x runs to infinity and go 2x power 4, divide it by x squared, 7 over x squared. Down below, it's x squared over x squared plus 7x over x squared. Next step we take is just simplify what we've got. So now we've got limit x to infinity. From up here, it's 2x squared. Yeah, go ahead.
Is there any difference in
If it's, oh, the value right here, it could potentially make a difference, absolutely. If this was power 5, we could be getting a different answer than positive infinity. It could have been a negative infinity. So yeah, that direction, negative infinity, does potentially matter on this one. But as far as the limit laws go, these all convey the same exact way. The author just wanted to state them once, but they're valid if x goes to positive or negative infinity. Other questions at the moment? Okay, I'm glad you asked that question again because that really does matter in some problems. So we'll make a big deal out of it as we get through this one. So here we have, after simplifying, 2x squared plus 7 over x squared, divide by 1 plus 7 over x. So that's our, sorry about that one, there we go. I'll get better at my windows as I practice this stuff. It's really hard to move a Microsoft window sometimes. There we go, Microsoft Word window. So this part here, 7 over x squared, and the 7 over x, even though they have a constant 7 on them, they're both just literally a 0 through this property here. The power on this one is 2, the power on this one is 1, both bigger than 0. So we'll say that that goes to 0, that goes to 0. The denominator is now identically equal to 1, and so it's all about what happens to 2x squared as x goes to infinity. Well, the larger and larger you put x in there, the bigger and bigger this would get. So this whole thing is just infinity itself, like was mentioned earlier. We could have spotted that by seeing that power is 4, but again, this is pretty, oh, hang on, pretty sensitive to being careful with positive infinities and negative infinities. Looks like I have an error right here. Let me correct this. It's a good color to show that there's a mistake. This red should do the job. We have the same value here of infinity, and that's only because if we were to graph our function, the one part that's left over, 2x squared, here's what it looks like. Doesn't matter if you go off to negative infinity in this direction or positive infinity in this direction, the values get higher and higher and higher, so we say infinity. But if it was a cube, notice the change there. Our answer would have been negative infinity, because we're going off to the far left, negative infinity on this one. For odd degree term, this goes lower and lower and lower. So this method of just dividing things out, see what's remaining, is really good on this one as well, because of the potential trickiness with negative infinity. Well, there's a lot of things to discuss here. We're going to come back to these notes and finish it when we come back on Tuesday's class. But any last questions or comments, folks, with what we've done so far? Okay, For the brave, I'd say you could start the WebAssign section right now, but you would find some problems right around stuff that looks like this, exponentials and the application problems. If you'd rather wait on those until we finish off the section entirely, it's not a bad idea. But just for staying ahead of things, it's probably not a bad idea to try a couple problems until you see some unfamiliar ones. And then you can wait on it till next class meeting. Also, the due dates on all these are going to be a 1 week turnaround. So we're going to finish it on Tuesday. The official due date will be pushed to January 28th in section 2.2. Well, that's all I have for folks so far. Sorry for running over the minute on this one. Have a great weekend, and we'll just be right back here where we left off on Tuesday's class. Have a great weekend, folks, and forgot it's a holiday weekend. Have a great holiday as well.